And I'm going to venture out on a limb for just a second, because James's presentation recalled something to me very, very poignant and very personal about something that happened a long time ago. Loretta Vinciarelli, who was an architect in New York in the late 1970s and worked with Donald Judd on some of this work, and I only know it because she taught me in so many ways how to draw, and so much of what she was teaching us were the kinds of wonderful drawings she was doing of these buildings in Marfa. I can speak nothing to her involvement of the technical details, but it is in terms of the power and quality of those buildings, always has resonated with me, and it was great to hear James talk about it in that way. So, but on to Louis Kahn and the Richards Laboratories. First of all, I want to thank the Park Service and NCPTT and the World Monuments Fund, all of you, for inviting us here today. We are honored and thrilled, and I think that given everything we've heard the last couple of days, I think there'll be some interesting material to add to the archive here. The Richards Lab, as many of you know, was a notorious building before it was even finished. Vincent Scully, at the time it was being designed by Kahn, clearly came right out and said that this is a landmark work in 20th century architecture. This is changing architecture. And the buildup was such that before the building even opened, it had a solo show at the Museum of Modern Art. So this is a very, very important building. It's a building about the integration of structure and systems, and the whole notion of servant and served spaces, which Kahn became so famous for, really came to the fore for the first time in this building. But what's poignant about it is you see this quote here. And what this is all about is, of course, that he really thought of laboratories as being like architectural studios, that people would want to work in these big, open, light-filled environments. And unfortunately, the nature of the programming process, whatever he went through at the University of Pennsylvania in the late 1950s, he didn't really get to talk enough to the scientists who were going to be using these labs, and consequently, from the day it opened, besides being internationally famous as a work of great architecture, it was famously dysfunctional, to the point where the University of Pennsylvania, the people who used this building, were threatening to just leave or blow it up or do anything. But I say that not so much to criticize the building, but to instill in you the need that we had to change things. This is an instance where it is a National Historic building. It is an iconic building. There are certain things you absolutely can't change. But there was much, especially programmatically on the inside, that had to change for the building to survive. So looking at Richards, basically the original Richards is the four buildings that the four blocks that have the letters in them. The blocks to the right are the Goddard Labs, which were designed also by Kahn, but built subsequently and under a little bit of a cloud. So a lot of the detailing that was realized there doesn't come up to what you have in Richards. But it's the idea of the servant. I'll just do it on this one side, and I apologize to the people over there because I know that's where I've been sitting. This is the servant, and these are the served. So you basically have essentially a brick box here, and these highly glazed towers surrounding it. Okay. It's not advancing, though. Okay. There we go. Sorry. Here's the building under construction. Kahn was very heavily influenced in the design of the structure of this by August Commandant. This was his first collaboration with August Commandant, a sort of visionary structural engineer who worked for 18 years with Louis Kahn and wrote a very sort of tell-all book about it some years ago. But here you see the building going up, and the idea of the very strong expression of this reinforced concrete structure with these precast Vierendeel trusses, which cantilever off the columns that really form the centers of each of the served bays. And the purpose of that was to open it up to the world at large, but also in the Kahn's notion of sort of creating community, being able to see into each other's lab, to be able to have this communication that is evident in this wonderful photo by Mildred Schmertz shortly after the building opened. The idea that these enormous windows allow light and quality to permeate from one side to the other. Here you see the actual plan, and with the thing that's important to remember, which we're not going to go into in this presentation, but is certainly a very important part of this story, is that the interior partition layouts within the glazed towers really were of no consequence to Kahn himself. As I said, his preference was to keep them all open. However, they did conform to a system which aligned, where the partitions really could be used on line with the structural grid, and here is a reflected structural plan of a typical floor. And you see these 4 squares within the 9 squares of each of the corners. And one of the things that we had to face was dealing with the fact that if you follow those lines, they don't meet Penn office standards, and I say that's a presentation for another time, but it was a very interesting challenge as to how we dealt with that in coming up with new schemes for the interiors of the building. And here, finally, for this introductory piece, is the sort of tinker toy pieces in construction going together. And you can see the extent of the cantilevers that you have here, and part of that, the movement, because of the concrete creep in those cantilevers and the expansion of the brick, are some of the things that we had to deal with in facing the changes to the glazing later on. Matt?
Thanks, Dave. Power through. So as David said, there were functional problems from day one, but this, another one of these almost construction finish photos, certainly gives a sense of what Kahn thought the spaces should look like on the interior. This is actually looking into Tower D from Tower C, so from the servant to the served towers. But you can also see in this image, in the Vierendeel truss system above, the organization of some of the mechanical systems that fed the building, which is what I'm going to talk a little bit about because it was also very important to the vision of the building. But this is what we were faced with going into the building. So this is how the building has been used pretty much since it opened up. And you can see the kind of overlay of systems and things that have been put in and the kind of degradation of the space based on what was, how it was being used. And as David said, this incredibly important kind of planarity of the exterior envelope and the way the materials met each other, which has been partially compromised based on minor movements that, particularly around the corners of the building as it relates to the windows. A critical element of, excuse me for a moment. A critical decision that the university made prior to our even engagement was the decision to change from wet labs to cognitive neuroscience in this building, which was going to take out a lot of the kind of systems pressure on the building and allowed us a lot of freedom in terms of how we were going to be designing the building and designing the systems. Our scope of work included an initial feasibility study and then renovation of just 2 floors of 2 of the towers. It was a limited scope, although they've now moved into a full renovation of the entire building. And Penn was not prescriptive about the solutions that they wanted, but they did provide a sense of their expectations. And just from the RFP, they stressed that they expected the high sensitivity and coordination between historic preservation, mechanical engineering, and space planning, and that the design should result in a high-performance, energy-frugal, light-filled, and healthy building. And I stress that word frugal because it gave us a sense that Penn, which is very aggressive in their energy reduction targets for their buildings, both new and existing on the campus, saw this as a potentially different project, that they were not mandating specific reductions, but they were asking us to be energy frugal, which was kind of a nice way to start the project. I just want to mention that David and I were backed up by an incredible team of people and firms, one of which I want to point to specifically on the envelope windows are a Heinches Associates out of New York, Areta Polinsky and Aaron Davis. Much of what they produced is critical to the presentation you're seeing today. But all of these people had to buy into the kind of design approach that we were developing, even though the systems and everything may be typically thought of as independent. And the final partner I want to mention is the construction manager, Intech, because many of the end solutions that were developed were only developed with the input of the contractor and the subcontractor to make sure that they would work. One of the things that we learned in the feasibility study was that to really be able to guide us in terms of how we were going to be dealing with the building was that we had to think about some basic design principles that Kahn and his team had developed in developing the design. One of which was how all the materials in the building, the junctions between them, how they meet each other, and how they terminate. These are snippets from some of the original construction drawings. This happens to show how 2 cinder block walls would meet, but also ahead of the typical door head window where you really only have jambs and you have no head to the window. And it really simplifies the lines of the building, and it was something we had to always keep in mind. On the mechanical systems, what was really critical in terms of the mechanical systems is that they were treated as a visual element in the building. And Kahn stressed the idea that, that the architect should understand everything about the structure and the systems and construction technology because it all had to be integrated into a whole. It was not thought of as separate components. And the layering in the mechanical systems, that section that's at the bottom of the screen, shows how the systems were layered in the Vierendale trusses, one, to highly organize them visually, but also to allow the systems to feed up to the floor above for electrical and telephone, and then for the mechanical systems to feed the level below, which meant that you had no systems that had to go through the zone that's created horizontally by the windows. It's a very, very important issue. This diagram is from Tom Leslie's book, Louis Kahn, Building Art and Building Science, and it shows just kind of the rigor of the layout of the systems and how it was worked into the Vierendale trusses, which again was something that we had to pay close attention to because we were going to be changing the building systems, but we had to think about what that meant in terms of these designs. A quick diagram, one of the key things that the university also wanted to explore was the idea of changing from their standard design HVAC VAV systems and go to chilled beam systems. The benefit of this was both energy savings, but also further reduce the size of some of the ductwork and the routing that we were going to have to deal with, simplified some of the coordination issues for us, and also had offshoot benefits specifically as it related to the window design. It also posed us with a problem, though, of we're going to have new objects in the space, and what were they going to look like? Chilled beams, there's not a lot of range of them available in the market, so again, thinking about how they are going to lay out in the building. We did all of the layout design of the systems in Revit. We used it as a design tool. We actually would use it in design meetings with the owner to understand exactly visually how this was going to look in the building.
So now we're into the windows. This is a construction photo, and I think it shows a late construction photo, but it's before they started to put in any of the interior partitions, and it emphasizes the vitrine-like quality of these windows and the incredible crispness and planarity of the system that Kahn was able to develop. And I've been doing a lot of research on this system, and it's quite ingenious. And this is where the no thermal break, no problem comes in, because it does not have a thermal break, but it is an incredibly elegant system. And given all of the sort of chatter that was happening in the 1950s and 60s about making very, very minimalist curtain walls, nobody really talks about just how good a job Kahn did in achieving precisely that. The building on the left is the AFFL Medical Services building that he did in Philadelphia. It was unfortunately torn down in the 1970s. But this is where he first began to develop this. Basically, it is a matte finish, brake metal, stainless steel folded plate system that he uses to create these windows. And there on the right, you can see a view down the window. And I also want you to take note, if you look really, really carefully, you can see a little bit how the brick wall comes out and the corner mullion comes in. And that kind of deformation in geometry was one of the really tricky parts that we had to deal with all along. These are details of very quickly going to go through the evolution of the Kahn's thinking about windows. These are steel windows in the first proposal for the AFFL building, similar to actually the steel windows he did at the Yale Art Gallery, which is, of course, a building that he had finished right before that. But as he's working through the design, he also proposes an aluminum alternate, and then finally goes forward with a folded plate brake metal stainless steel system. Here are the design drawings, and then here are drawings, detailed drawings from the actual construction and submittals that went through into construction. So he's thinking very hard about this and sort of working on this idea of creating this incredibly sheer surface, because there are no tubes, there are no, the sections are very, very light, and they get all their strength from just being folded. So here now is a detail sheet from the Richards Laboratory, and you see first of all, the size of these lights. They're almost 14 feet by 5.5, the big ones, and they were just 1/4-inch polished plate. And then the dark sections that you see in the upper right-hand corner are the actual profiles, a jamb at the top and the sill at the bottom of these. You can see how incredibly minimal that is, and very, very little. The only projection really from the surface is where they had tracks for exterior shades and a very, very minimal drip. This is, again, some of the details more fully developed. You see with the cool shade on the left, that's the tracks that overhang, and this very, very elegant corner mullion. Now, part of our mandate, and here is a view of an original window, and I wanted to just point out something that does not appear in the drawings but does appear in construction, which are these little stainless steel clips, because that's something that we talked about in terms of when we got to the point where we had to replace the glass as to whether or not those were to be replicated. So this is a pretty good look at an original installation as it stood about 2 years ago. Again, the proportion of the wall, you can see there the numbers laid out, so that obviously we're dealing with a very, very high energy loads on this building. One of the things that people always talk about when we say we're working on this is, oh yeah, that's the building that's covered with tinfoil, because there was very little in the way of sun control that went along with this, and that was, again, part of our mandate. But one of the things I just want to point out very briefly is that there is also in the slots between the towers a very early use of an IGU. These are with these sort of welded metal seams, and most of them, not all, but most of them have held up very well, certainly better than you would expect a contemporary IGU being 52, 53 years down the road. So looking here at again at the existing condition, a typical section on the left, typical plan at that very, very elegant corner on the right, and obviously a big energy sink. So one of the things that we had to do, since Penn, like many institutions, is sort of trying to adhere to a mandate to achieve 30% energy reduction in a fairly short period of time. There's a large number of universities around the country that have signed on to this. And so they're looking at every project with the idea of what can we do to be frugal, as Matt said, as possible. They weren't demanding, but they said you have to explore every alternative. So we did look. We said, okay, can we somehow mimic these profiles in a thermally broken frame? Well, there are two problems with this. One is the frame really is a little, or three. The frame is a little bulkier, or maybe way bulkier than we would want it to be. Two, and most important, you're having to rip out the original frame, which means you are disrupting both the concrete frame and the brick infill around it. And three, you still have the problem at the corner of the lack of a thermal break. So it's never going to be a perfect solution. So we continue to develop, and again, looking on the left, that's the existing. In the center is saying, okay, well, what if we keep the frame, but still try to introduce an IGU? And this was just deemed to be too tenuous for a lot of reasons. And a lot of that had to do with the fact that of the distortion that was playing. And, and it's hard enough to take up distortion in a monolithic piece of glass, but to try to do it in an IGU, because none of the replacement lights of glass were actual rectangles. They were all, they all had deformed corners of one kind or another. So on the right, what we eventually came up with, and this echoes a little bit of what Walter said yesterday, the use of high-performance laminated glass, the idea that we could get with a laminated glass a significant improvement in performance over the quarter-inch polished plate, a more permanent solution because it does not have the problem of the degradation of the seals, and the ability to both put an interlayer in this which would help in terms of solar control, still invisible, and keep it flat. It was very, very important, the flat quality of this glass, which you're not going to get with an IGU, and you're not going to get with tempered glass because of the roller wave phenomenon. But it is possible to do that with laminated glass. Here at the transom, one of the things we had to deal with the laminated glass, which you see on the right, was worries about the possible exposure of that piece of film at the intersection between the two lights. We did some testing on that. That was determined not to be an issue with the glass, and so we went forward with that.
Just quickly, we did do energy analysis on the building overall. Our engineers really drove this. And this was helpful in kind of helping Penn come to grips with the decisions that they had to make. I didn't mention before, we had a number of constituencies at Penn. We worked for Facilities and Real Estate Services, which is where the campus architect's office is. But the building is occupied and essentially owned by the School of Medicine. So the funding for the project came from the School of Medicine. And their priorities weren't all the same in terms of what they were trying to achieve out of the project. But you can see we did do a study of different kind of ways of looking at the building in terms of systems and glazing. And this was an early pass at understanding what kind of energy reductions we were going to get from the design. And essentially the one on the left was the existing energy usage, and the one on the right was using chilled beams with IGUs. And you could see that that's obviously the best option in terms of energy reduction. But the difference between that and just and using chilled beams with a laminated glazing wasn't significant enough. The greatest energy savings was out of the mechanical systems upgrades and not out of the glazing. And so it allowed Penn to kind of sit back and think that, well, maybe the preservation issues in this case were enough to drive the decision because they were getting significant energy benefits out of the other elements of the design, and that satisfied them. We also did testing on the windows. We wanted to understand whether we were really achieving the improvements that we were planning on doing. So we did both air and water infiltration testing on the existing windows, and I always like to say that they failed magnificently. The air infiltration, based on the size of the window and the configuration, we would be allowed about 18.5 CFM as an allowable for a window installation. We were over 35, and they could barely get that because they couldn't keep enough pressure in the chamber to figure out what the number was. And on water penetration, the test is supposed to run for 15 minutes. We stopped at 4 minutes, 15 seconds because we were probably going to flood the lab space below. The good news is that after the mock-ups were done, we retested the new installation, and the CFM is down to below 1 CFM, well below what is allowable. And water penetration identified some weaknesses in workmanship that we were going to have to deal with in full installations, but really was at a level that was low enough that positive pressurization of the building with the mechanical systems would deal with that and was not going to be an issue.
So now we're getting to the actual mock-ups and installation. So the first thing we did was look at the glass itself. And because of the scale of these lights, we decided to make the glass choice prior to fabricating the full 14 by 5.5 foot units. And we worked very closely with a couple of glass manufacturers, eventually settling on Viracon, looked at both the VLE 70 and VLE 85, looked at combinations of low iron and clear glass against 2 layers of clear glass and the laminate, and finally came up with the closest match being the VLE 70 with a low iron on one side and a clear glass on the other side. Virtually identical to the original in appearance, but much, much more robust. Then we also looked at just in terms of the restoration of the steel itself, looking at that corner. The steel was in excellent condition. There was no corrosion to speak of, and they were really the only things that we really had to do with it was lightly clean it, because it is this very matte finish, a finish that Kahn would grow increasingly fond of as he worked through his career. This very, very almost pewter-like stainless steel finish. And so it was really just a matter of repassivating the areas where we were going to be reglazing and doing a very, very light cleaning on the rest of it. And then on the right, you see the first of where we did do a full corner mock-up, 2 lights of glass, two of the big lights, and all of the transom lights. Looking up at the corner, there you see it without the clips. The reason we decided not to use the stainless steel clips is because they were not part of Kahn's original detailing. They were done for expediency because of concerns about how well that corner could actually be sealed, and we didn't feel it was honest to put them back. They would be purely decoration. And we felt, frankly, it's one of those things too, if anybody feels strongly enough about it in the future, you can go up and glue them on, which is all they'd be anyway. But the technology that one uses to butt glass these days is far advanced from what it was in 1961, and so we felt quite comfortable leaving it the way it is, and as I say, a more honest approach. There was a lot of discussion about exactly how to set these windows. We tried initially to do a mechanically fastened stop on the inside. We spent literally hours in the field arguing over 1/8, 1/16 of an inch tolerances and dimensions to try to get this to be just right. And in the end, what we ended up with was a structural silicone ceiling. We're using a Dow 995 silicone to set the windows, and the aluminum stop is adhered with a VHB 20mm020 VHB tape, but it really is not performing any structural function at this point. And here is the midst of that discussion that I talked about, where we were looking at this. So I think it's a tribute to the designer, the specific designer of the glazing, Aaron Davis, who's there on the left from Heinz's, and I think also to the fabricator and installator, the people who put these things in and who were able to get the tolerances to such a way to accommodate all of the deformation in a way that still pass, as Matt said, the test that we've run on these windows post-installation. And here's where we are today, where the windows have been installed. They are temporarily braced until we get the stops in, just as a matter of precaution. But really, the building from the outside doesn't look any different. It just looks a little bit cleaner. And I think once we're done on the inside, the differences, if you're going to notice differences, it will be elsewhere in the building and not in the glazing. Thanks.